Now, if a function is differentiable at a given point, that means it's possible for you to draw a tangent line to the function at that point. When you zoom into the point, so as you get closer and closer to the point, it starts to look more and more like a straight line. So your function is what we call locally linear. Now we are going to exploit that property today. We're going to solve some very interesting problems by making use of the fact that you can draw a tangent line to a differentiable function. And so a couple of things that we're going to talk about today, but the first one is this idea that a function can be swapped or replaced by its tangent line at a given point. It's usually much easier to work with the equation of a tangent line rather than some other function. And there are going to be some situations where you don't even know the equation of your function. All you have is a limited bunch of information, so you have no choice but to use the tangent line instead. To begin with, we take a function, f of x, and we are going to focus on trying to come up with the equation of the tangent line at a given point. So if we were to draw in a function like this and say, let's use this location A, the tangent line we simply draw and we figure out the equation of our line like we normally would. So y minus y1 is m x minus x1. Now here x1 is a, y1 is f of a. So far we've got y minus f of a is m into x minus a. And the point of calculus, really, one of the main objectives here is to say that if you have a function that's differentiable at a point, you know that its slope is given by f prime of a. So we've got the following. If we were to reorganize this for y, we would have y is f of a plus f prime of a times x minus a. So this would be the equation of the tangent line to the function at the point x equals a. We are going to call this a linear approximation to the function f at the point x equals a. So rather than calling it y, which you completely could, sometimes you're going to see this notation L of x. And we will write down this formula. It's just the equation of the tangent line. This point A is called the center of the approximation. This is the point at which you will essentially extract all information about the function and then use it to build your line. Once you've built your line, then that point A is kind of fixed, and then you can use other points, x, and use the line to make approximations. So to try to illustrate that to you, here's an example. So I'm going to take a relatively complicated function, so 1 plus x to the power of k. And I'd like to build a linear approximation to this function centered at the point x equals 0, and then I would like to use that approximation to make some estimates. We're going to assume that k will be some positive number for now. So if we were to take this essentially looks like a power function. It's kind of been shifted, so it crosses the x-axis at x is -1, and when x is 0, we will have a height of 1, regardless of that power of k. We have been asked to build a linear approximation to this function centered or using x equals 0 for all of our information. So if we were to build a linear approximation, it would kind of look like this. Now, this formula, it's just the equation of our tangent line. 0 would be that value. F of a in this case would be 1. And so we'll have y is equal to 1 plus f prime of a x. Now in our case, the a is 0. So we're going to need to figure out the derivative of this function. F of x is 1 plus x to the power of k. So if we were to use the chain rule and differentiate this, we would get k 1 plus x to the k minus 1 and then the derivative of the inside stuff would just be a 1. So f prime of 0 means k 1 plus 0 to some power, and that's just going to end up giving us a k. So the linear approximation is just the equation of the tangent line. It's going to be 1 plus kx. So in terms of the picture, here's our function f of x, and here's our linear approximation. So I would like to estimate this value, 1.0002 to the power of 50. Now note, my original function was 1 plus x to the power of 50. Based on this, I can see that I should take this and think of it as 1 plus 0.0002 all to the power of 50. So if I want to use the linear approximation, I'm going to then say, okay, I want to stand right here, 0.0002, because this number is equivalent to me picking a value of x and then adding 1 to it. Well, the value of x that I want to use is 0.0002. So if I want to estimate, I will take that value and plug it in. Okay, so I go ahead and I calculate L of 0.0002. According to my linear approximation, k is 50, and I'll get 0.0002. 0.2 is 1/5. 0.02 is 1/50th, 1/500th, 1/5000th. So I'll get 1 plus 1 over 100. This is 1.01. So I will estimate that 1.0002 to the power of 50 is approximately 1.01. Now, it's a simple matter for you to take a calculator and get the true value. So if you were to take your calculator and plug in 1.0002 to the power of 50, your calculator would tell you 1.0100491573, blah, 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 blah. And you can see that we've got 1, 2, 3, 4 decimal places correct. So this estimate is correct to 4 decimal places. That's pretty good. If I wanted to estimate the value of 2.0002 to the power of 50, remember that this would be 1 plus 1.0002 all to the power of 50. I have to put this in the context of the function that I want. So that means I have to use L of 1.0002 to estimate this. And when I take my linear approximation and I plug this in and I do my estimation, I will get 51.01. So I say, oh, that's great. I'm just for fun going to compare it with the true value. And the true value, 2.0002 to the power of 50, I figure, okay, I'm not going to be that bad. Wrong. If you take your calculator, you're going to get 1.131 times 10 to the power of 15. 10 to the power of 6 is millions. 10 to the power of 9 is billions. 10 to the power of 12 is trillions. This is about 1 quadrillion. That's a lot bigger than 50. A lot bigger than 50. So, what went wrong? The idea is that the linear approximation is only valid near the center. And we can see this a lot more clearly when we take a look at the graph. And we'll introduce some more terminology here. So the function here has its tangent line, and they kind of look like this. Our center was 0. So when I stood at 0.0002, and then I stood there, I said, oh, okay, let's take a look at them. And you can see from this picture that those two dots aren't that different. But if I were to go over here, 1.0002, when I did the second estimate, you can see that those two dots are completely different. Much, much different. Much, much more different, I should say. This is the center. The closer you are to the center, the better the approximation will be. Now, if we want to try to introduce some ideas behind this amount is called df. This is the amount that the linear approximation changes if we go some distance delta x. So if I say, okay, let's go and measure this distance right here, just for an example in the second situation, let's call that delta x. If I were to talk about the same thing, I'll call this delta f. Delta f is the amount that the function changes over some distance delta x. And to put it in terms of this terminology here, delta f, df will be approximately equal to delta f if we are near the center. So that means if delta x is small. In the first example, this was my delta x. It was very small. And then the change in height, df versus delta f, was also very small. The two of them were very close. In the second situation, the delta x was not close at all. And that means I should not expect the differential. So this thing here is called the differential to be very close to the actual change in the function. The closer you are to a point that you're using as the center, the better and better your linear approximation will be. The further away you go, the worse you expect your approximation to get. Now, just as a little side note, you can use the differential to approximate changes in the value of a function over some distance delta x. And it's kind of all predicated on the fact that, all right, if you take this to be your center, that's your starting point, we will take this distance here to be delta x. We are going to assume that this is your tangent line, and this point right here is the center. So we know that the slope at the center is f prime of a, and we know that slope is rise over run. So that means if we put this all together, f prime of a is the slope, the run is this delta x, and the rise is just going to be the differential, because we are building ourselves a little right triangle, and this is the linear approximation. So we'll have a df, and then we could easily calculate the df is just f prime of a delta x. So if we wanted to, if we were ever asked to estimate the change in the height of a function, we can simply just use this differential idea, but it's all based on a linear approximation anyways.